Okay, so today we're going to be doing Laurent Series expansions, and even though they're not that common in exams, they do appear occasionally, so they're well worth getting to know. Basically, Laurent Series expansions are very similar to Taylor expansions. So just as a reminder, very informally, a Taylor expansion has around a point x equals a, has terms of the form x minus a to the n. A Laurent series expansion, as well as having terms of the form x minus a to the n, also has terms of the form x minus a to the minus n, and that's the basic difference between the two. Okay, so let's get on with the questions here. So question number one, we've got f of z equals 1 over 1 minus z, and we need to find the Laurent expansion A in the region mod z less than 1 and B in the region mod z greater than 1. Okay, so let's just have a look at this little diagram here. Now, if we notice in our function, there is a singularity here at z equals 1, but neither of these regions actually include z equals 1, and therefore both of the regions are analytic, and therefore we can do the expansions about them. That's the first thing. The second thing is that as we are expanding about both of these regions, we are actually implicitly expanding about the point z equals 0, so we will be finding terms of z minus 0 to the n and z minus 0 to the minus n, i.e. z to the n and z to the minus n. Okay, so basically, let's have a look. Now, the first one, f of z equals 1 over 1 minus z in the region mod z is less than 1. Okay, well, in the region mod z less than 1, that means z is less than 1, which means it's a very simple one, this. 1 over 1 minus z basically is just using the geometric series 1 add z squared add z to the n, which would add which we know converges because we are told that A, this region here, z is, the modulus of z is less than 1, and therefore we know that it converges. So this is an entirely Taylor series. There's no need for any Laurent terms because there are no terms of the form z to the minus n. These are all terms of the form z to the power of positive n. So that's the answer to question 1a. Okay, now let's have a look at question 1b. What we're doing now is we're doing it in this rather nice looking, I'm not 100% sure what colour it is, brown thing. That's the region mod z is greater than 1. Once again, the singularity z equals 1 does not appear within this region, and therefore it is analytic. Now, the problem is, because mod z is greater than 1, therefore we cannot use the geometric series here, because it would mean that it doesn't converge, because we need that to be less than 1. So what we do is we do a little trick. Okay, so basically what we say is, okay, 1 over 1 minus z equals 1 over, let's take z out as a factor at the bottom, and that gives us 1 over z minus 1, and that equals minus 1 over z 1 minus 1 over z, okay, which is equal to minus 1 over z times by 1 over 1 minus 1 over z. Now, for the region mod z greater than 1, if mod z is greater than 1, then mod 1 over z by definition is less than 1, which means that we now can expand this bit by the geometric expansion, geometric series, because we know that it will converge, because 1 over z definitely converges when mod z is greater than 1. That's actually quite a common trick that we see fairly often in Laurent series. So basically that equals minus 1 over z times by, and this, here all we do is we just expand this, 1 add 1 over z, add 1 over z squared, add add 1 over z to the n, and then when we just multiply this out, that gives us equals minus 1 over z minus 1 over z squared minus minus 1 over z to the n plus 1, well, minus ad infinitum. And we can see that this is a Laurent series because all of the terms here are of the form z minus 0, or i.e. z, to the minus n. So basically this is a Laurent series expansion. Okay, so that's that one. That was a nice easy start. So now what we're going to do is we're going to get slightly more complicated here. Let's have a look at this second one here. Okay, so we need the Laurent series expansion. Again, it's told us around z equals 0. So we're looking for either the form zn if it's Taylor, or z to the minus n if it's Laurent, of this function here, A, again, in the region mod z between 0 and 1, and this is slightly different from the first question, and I'll explain that in a second, and B, the region mod z greater than 1, which again is this nice little brown region here. So this region here, mod z greater than 0 and less than 1, remember in question 1 it was just mod z less than 1, so in question 1 that included the point 0, whereas here this does not include the point 0, i.e. that red thing there is not included in the region, and there's a good reason for that, because if we look at our function, there is a singularity at z equals 0. Also there's a singularity at z equals plus or minus I, and therefore if any of these singularities were within our region, then the function wouldn't be analytic. But because we have specifically excluded 0, and also we have excluded the point mod z equals 1, therefore I minus I, which are those 2 points, and 0 are all excluded from both regions A and B, so therefore we know the function here is analytic, so we can go and expand it. Okay, so now that we've done, that's important, we have to make sure that it is analytic before we bash on. So let's have a look at how we're going to do this. Okay, well basically in the first instance, 0 less than or equal to mod z less than 1, well we have 1 over z squared plus 1, and let's just rewrite that as 1 over z squared times 1 over 1 minus z squared. We now have this in the geometric form, and as we have mod z is less than 1, we know that z squared is going to be less than 1 as well, which means we know that this is going to converge, and therefore again we can use our geometric series, so that would be 1 over z squared times by 1 add minus z squared add minus z squared add minus z squared cubed add minus 1 to the n times z squared to the n add Okay, and all we need to do now is expand this bracket. That gives us 1 over z squared minus 1 add z squared minus z to the 4 add z to the 6 minus blah 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 add minus 1 to the n times z to the 2n minus 2, which basically, writing it in summation form, that would be the sum between infinity and n equals 0 and infinity of minus 1 to the n z to the 2n minus 2, and we've already established that that is valid as long as mod z is less than 1, which is region A, and as long as it doesn't include the point 0. And just to confirm, this is a Laurent series because it has a term in the form z to the minus 2. It also has terms in the form z to the plus whatever, which is the Taylor part of it. But as it has terms in the form z to the minus, then it is called a Laurent series. Okay, so that's question number 2A. Now question 2B, we're going to do exactly the same thing, but in the region mod z greater than 1, and we're going to use the same trick. Obviously what we can't do here in this bit, for mod z greater than 1, we can't use the geometric series because it doesn't converge. So what we have to do is the same trick that we just did in question 1, which is that if mod z is greater than 1, then mod of 1 over z is less than 1. So we need to rearrange it to get it in the form mod 1 over z. So basically we know the singular, well let's just check the singularities again. We have singularities at z equals 0 and z equals plus or minus I. Well, mod z greater than 1 does not include any of those singularities. We've already established that. They're those three, and they're not included in the region mod z greater than 1. So therefore it is analytic, and so therefore what we can do is we can go, okay, 1 over z squared plus 1 equals, okay, so what we're going to do is we're going to take z squared out of here, which leaves it as 1 add 1 over z squared, which equals 1 over z to the 4 times 1 minus 1 over z squared. And now we have it in the geometric form, and we know that the modulus of 1 over z squared is less than 1 for reasons that we've just established, so we can use the geometric series, and so therefore our Laurent series expansion is 1 over z to the 4, 1 minus, okay, minus 1 minus 1 over z squared, add minus 1 over z squared squared, add minus 1 over z squared cubed, add add minus 1 to the n 1 over z squared to the n, add ad infinitum. And now when we multiply out, we get 1 over z to the 4 minus 1 over z to the 6, add 1 over z to the 8 minus 1 over z to the 10, etc., etc. Add minus 1 to the n 1 over z to the 2n plus 4, add and to put that in summation form, that is the sum between n equals 0 and infinity of minus 1 to the n 1 over z to the 2n plus 4. And again, this is a Laurent series because we have all of the terms, well, some of the terms, as it happens in this particular case, all of the terms in the form z to the minus n as opposed to z to the n if they were Taylor. So that is the answer to question 2, part 2. Okay, we're doing well here. Right, let's have a look at question 3. Find the Laurent series expansion of this. F of z is 4z over z minus 1, z minus 3 squared in the region mod z greater than 1 and less than 3. Now, let's just have a quick chat about this region here. It's an annulus, which we've drawn on the right hand side here. So basically here is the point 1 and here is the point 3 and here is the point minus 1 and here is the point minus 3. So the region is this pink annulus thing. And let's have a look at the singularities. We have a singularity at 1, i.e. z equals 1 here, there's a singularity. And we also have singularity at z equals 3 here. But because we are in the region mod z greater than 1 and less than 3, those two singularities are not part of our region and therefore we can expand it. Also just note that the centre about which we are expanding is again 0 because that's the centre of both circles. So again we'll be looking for terms of the order z to the n and z to the minus n. Okay, now the first thing we got to do here is we got to split it into partial fractions. So let's go and do that. So we got 4z over z minus 1 z minus 3 squared equals a over z minus 1 add b over z minus 3 add c over z minus 3 squared. That's the standard way of doing partial fractions when you've got a square in there. And basically what we need to do now, so that'll be just comparing the top, that'll be 4z equals a times z minus 3 squared add b times z minus 1 z minus 3 add c times z minus 1, and expanding all this lot out gives us 4z equals az squared minus 6az add 9a add bz squared minus 4bz add 3b add cz minus c. Okay, now comparing coefficients of z squared, we get that a plus b equals 0, and let's call that equation 1. Comparing the coefficients of z, we get that minus 6a minus 4b add c equals 4, and let's call that equation 2. And comparing the constants, we get 9a add 3b minus c equals 0, that's equation 3. Okay, well let's just do what we're going to do here. Let's just do 3 plus 2. So equation 3 plus equation 2, that gets rid of the c, so that gives us 3a minus b equals 4, and then comparing that to equation 1, we get that a equals 1, b equals minus 1, and c equals 6. Okay, so the partial fractions come out quite nicely, and so now what we have is that our function that we wish to expand is equal to 1 over z minus 1 minus 1 over z minus 3 add 6 over z minus 3 squared. Okay, and now what we need to do, let's just remember that the region is mod z is greater than 1 and less than 3. Okay, so let's have a look at each one of these fractions one by one. Let's have a look at 1 over z minus 1. Now clearly, because z mod z is greater than 1 and less than 3, we cannot expand this as part of the geometric series on its own because it doesn't converge. So again, we have to use exactly the same trick. So let's just have a look. 1 over z minus 1. We can use the same trick we used in question 1 and question 2. Let's take z out, so that'll give us 1 over z, 1 over 1 minus 1 over z. And because mod z here is greater than 1, we know it's less than 3, but it's greater than 1, therefore mod 1 over z is less than 1, and therefore this we can use the geometric expansion, and so therefore that is going to be 1 over z times here 1 add 1 over z add 1 over z squared add add 1 over z to the n add So that basically is going to be, expanding out now, 1 over z add 1 over z squared add 1 over z cubed add add 1 over z to the n plus 1 add which of course is a Laurent series there. So we got that one. Now let's just put that as a sum, because obviously we're going to sum them up. That is equal to the sum between infinity and n equals 1 of z to the minus n. So that is our 1 over z minus 1, and that is a Laurent series. Now let's have a look at minus 1 over z cubed. Okay, so minus 1 over z minus 3. So minus 1 over z minus 3, what we need to do is we need to just rearrange this slightly. Let's just take out the third, so it'll be minus 1 over 3 times by 1 over 1 minus z over 3. All I've done there is I've taken the 3 out of there and is that correct? Let me have a look. Sorry, minus 1 over z3 is plus, isn't it? That's right, I knew there was a problem there. So that's plus 1 over z3 there. Now, because mod z over 3 needs to be less than 1, well, that would mean that mod z must be less than 3. And we know in our region here that mod z is less than 3, and therefore we're okay on this. So we can expand this one out normally. And so basically that gives us that minus 1 over z minus 3, we can just expand this one out as a Taylor series, equals 1/3 the sum between infinity and n equals 0 of z over 3 to the n. That's just a straightforward geometric series. Okay, good. So we got that. Now, here's the interesting one here. We need, what's the third one? There, 6 over z minus 3 squared. Okay, now the way we're going to do that is we are going to differentiate this. Okay, so the differential with respect to x of minus 1 over z minus 3, which equals, is equal to 1 over z minus 3 squared, which is what we want here. So basically, if we differentiate our series here, we get what we want without the 6 on the top. Okay, now that equals, now all we've got to do is differentiate this, 1/3 the sum between n equals 1 now, because the first term will be got rid of in the differentiation, of, let's differentiate each of these terms, n, z to the n minus 1 over 3 to the n. Okay, so basically we know that 1 over z minus 3 squared is equal to that. So therefore 6 over z minus 3 squared is equal to 6 over 3, the sum between infinity and n equals 1 of nz, n minus 1 over 3 to the n, which equals, let's just replace the n equals 1 by n equals 0. That will be 6 over 3, the sum between infinity and n equals 0 of n plus 1. All I'm doing is moving the indice from 1 to 0. N plus 1 z to the n over 3 to the n plus 1. Now we're almost there now. We need to just put all of this together, okay, to get the Laurent series. So basically what we have for the whole Laurent series, we have that it is equal to the sum between n equals 1 and infinity of z to the minus n, that is the 1 over 1 minus z bit, add 1/3 the sum between infinity and n equals 0 and infinity of z to the n over 3 to the n, add 6 over 3 the sum between n equals 0 and infinity of n plus 1 z to the n over 3 to the n plus 1. Now they basically are that one, and that one there, which is basically the sum of the three partial fractions, which themselves is basically that function there. Okay, so all we need to do now is just tidy this up. We're almost there now. So basically, there's not much we can do with the Laurent part. It's integral between n equals 1 and infinity of z to the minus n. Add, okay, well, let's just see if we can tidy this up. That's the sum between infinity and n equals 0 of z to the n over 3 to the n plus 1. That's that one. Add 2n plus 1 z to the n over 3 to the n plus 1. So basically now I'm just merging those two sums, z to the minus n, add the sum between n equals 0 and infinity of 2n plus 1 z to the n over 3 to the n plus 1. And that is our Laurent series expansion of the function. Now just basically having a quick look. This here, because we got the z to the minus n here, is the Laurent series bit, and this here is the more traditional Taylor series bit, because all the n's here are positive. Just as a matter of interest, more formally, this bit here is called the principal or singular part of the Laurent series, and this bit here is called the analytic part of the Laurent series. Okay, well, hopefully these 3 or 5 actually, because there were had two parts, hopefully they've proved useful. You know, basically all you need to do is take a lot of care knowing when you should use this trick. This trick we used in all 3 is where you basically replace z by 1 over z, in order that when mod z is greater than 1, mod 1 over z is less than 1. That's a really useful trick in this Laurent series expansions. You tend to use it quite a lot. Otherwise, you just got to be very careful that there are no singularities in the region. If there are singularities, then it's another kettle of fish, and we will deal with that in another video. Okay, well, I hope you found this useful. If you have, please like the video and subscribe to the Gresty Academy YouTube channel. Thank you.